welcome to this session. Now we will be solving the problem that generalized three-dimensional problem that we are solving. We have taken up in the last class. We will be completing it. We have already solved completely the sub problem theta 1. In the sub problem theta 2, we have completely solved the steady state part, which is nothing but an elliptical partial differential equation. Then let us look into the time varying part. If you look into the solution of the time varying part, it will be having a non-zero initial condition, and the rest boundary conditions are all homogeneous and Dirichlet. So therefore, we have already solved this type of problem in the first sub problem, and I will be directly writing the solution of that. So theta to tau will be nothing but summation of m summation over n Cmn exponential minus lambda mn square tau sin n pi x sin m pi y, and that at tau is equal to 0, we have the initial condition theta tau will be nothing but minus theta 2s, which will be the solution of the steady state part. So we put it there. So this becomes minus theta 2s is equal to summation over m summation over n Cmn sin n pi x sin m pi y, and we will be evaluating the constant Cmn by using the orthogonal property of the sine function and the eigen functions that we have done already before. That what is the solution of theta 2s? Theta 2s is minus 2 theta 1 naught, n is equal to 1 to infinity 1 minus cosine n pi divided by n pi sine hyperbolic k n pi x divided by sine hyperbolic k n pi sine n pi y. So that was the solution of the steady state part. That should be equal to double summation 1 over m another over n Cmn sine n pi x and sine m pi y. So we multiply both sides by sine m pi x and sine n pi y dx dy and integrate. After opening the summation series, only one term will survive in the right hand side, and that will be and the other will be lost, will be gone. So it will be minus 2 theta 1 naught some function of x and y. So I write this as some function of x and y is equal to summation m n Cmn sin n pi x sin m pi y. So this will be nothing but minus 2 theta 1 naught double integral over x over y f of x y sin m pi x sin n pi y dx dy. On the right hand side we will be getting Cmn. There will be one integral sine square n pi x will be half, integral sine square m pi y dy will be half. So there will be half there. So if we do that, then we will be getting an expression of Cmn, and Cmn will be minus 8 theta 1 naught from 0 to 1 integral y is equal to from 0 to 1 f of x y sin m pi x sin n pi y dx dy, and the index m was associated with y and index n was associated with x in this particular problem. So we convert them back to n and m, our normal variable. So this becomes 8 theta 1 naught x y f of x y sin n pi x sin m pi y dx dy, this will be minus 8 theta 1 naught 0 to 1 0 to 1. Now let us put f of x y. F of x y is nothing but 1 minus cosine n pi divided by n pi sine hyperbolic k n pi x sine hyperbolic k n pi sine n pi y sine n pi x sine m pi y dx dy. So you will be getting and so this will be giving you a some constant some value. So it will be you can obtain the CMN quite accurately. So once we will be getting the estimating the CMN, similarly the other sub problems which will be having a 0 initial condition and non-zero boundary conditions, they can be converted into a steady state part, and they could be divided into steady state part and the transient part, and that will be we will be able to solve them. So once we do that, then let us so that completes the problem that we were dealing with. Now let us go to the other problem. Now I will be taking a typical problem that we have not talked about earlier. So this is a second two-dimensional problem. So we take up another example. Let us say a two-dimensional problem, a parabolic one, two-dimensional parabolic partial differential equation, like del u del t will be is equal to del square u del x square, and at t is equal to 0 we have, let us say, u is equal to u naught, and the boundary at x is equal to 0, it is insulated. So it will be del u del x will be equal to 0, and boundary at x is equal to 1, we have a mixed boundary condition del u del x plus beta u is equal to 0. So if we remember that in the previously we have looked into the a problem where the both x is equal to 0 and x equal to 1, we have a dirichlet boundary condition, that is the problem of first kind. Problem of the second kind was at x is equal to 0, del u del x is equal to 0 and x is equal to 1, u is equal to 0, and problem of third kind was at del u was at x is equal to 0, u was equal to 0, and del u del x plus beta u will be 0 at x is equal to 1. So it is a mixed boundary condition that is prevailing at x is equal to 0. Now this particular problem, we have a Neumann boundary condition at x is equal to 0 and a mixed boundary condition at x is equal to 1. So that we have not attempted this problem earlier. So let us look into the solution of this particular problem. So again we will be going ahead with a separation of variable type of solution. U is a function of space and it is a sole function of time. So if you put it there, so this becomes x dt dt and x and t d square x dx square. Now if you divide by xt and separate out the variable, this becomes 1 over t dt dt is equal to 1 over x d square x dx square. The left hand side is a function of time, the right hand side is a function of space, they are equal and they will be equal to some constant in order to have a non-trivial solution. Now let us constitute the eigenvalue problem in the x direction. The eigenvalue problem is d square x dx square plus lambda square x is equal to 0, and at x is equal to 0 dx is equal to 0, and at x is equal to 1 we have dx plus beta x is equal to 0. So this formulates the standard eigenvalue problem in the x direction, and let us look into the solution of this. Now as we all of us know, the solution of x varying part will be constituted by combination of sine and cosine function. So x n is equal to c1 sine lambda x lambda n x plus c2 cosine lambda x lambda n x. So corresponding to nth eigenvalue we will be getting this solution. So now dxn dx will be nothing but C1 lambda cosine lambda n x minus C2 lambda sin lambda n x, and dxn dx evaluated at x is equal to 0, sin 0 is 0. So, the term that will survive is C1 lambda cosine lambda. Okay. So, that will be equal to 0 at this boundary. So, therefore, lambda n C1 lambda n cosine lambda n will be equal to 0. So, in order to have a so cosine at x equal to 0, so cos 0 is 1. So, this will be multiplied by 0. So, will be having cos 0. So, C1 lambda n will be equal to 0. So, for a non-trivial solution, lambda n cannot be equal to 0. If it is equal to 0, then we will be landing up with a trivial solution. So, the solution is C1 is equal to 0. If C1 is equal to 0, let us say what is the solution of this? Solution is C2 cosine lambda n x. Now, these are the eigenfunction of this particular problem. Now, let us look into the eigenvalues. How the eigenvalues are obtained? The eigenvalues are obtained by the boundary condition we will be putting at x is equal to 1. So, at x is equal to 1, it should satisfy the original boundary condition of the original problem. So, it will be dx plus beta x is equal to 0. If we look into the nth eigenvalue, so there will be dxn dx plus beta xn will be equal to 0, and xn is equal to this. Let us say what is dxn dx. Dxn dx will be nothing but minus C2 lambda n sin lambda n x, and at x is equal to 1, this becomes dxn dx is equal to minus C2 lambda n sin lambda n, and xn at x is equal to 1 becomes C2 cosine lambda n. So, then we will be substituting this into the boundary condition at x is equal to 1, and let us see what we get. What we will be getting is that minus C2 lambda n sin lambda n plus beta C2 cosine lambda n is equal to 0. So, therefore, C2 is in common. So, beta cosine lambda n minus lambda n sin lambda n will be equal to 0. So, C2 is equal to beta minus lambda n tan lambda n will be equal to 0. So, in order to have a non-trivial solution, C2 must not be equal to 0. So, the only option is lambda n tan lambda n is equal to beta. So, lambda n are nothing but the eigenvalues of this transcendental equation. Roots of this transcendental equations are the eigenvalues. Now, this lambda n and tan lambda n equal to beta, it will be intersecting the lambda n axis at n number of locations. So, if you really plot it, so this will be it will be cutting the x axis at infinite point, and each of the intersection point is a root of this particular equation. This can be also solved numerically by using a Newton-Raphson method. So, typically this type of equation, the roots are appearing in an arithmetic progression of common difference 3. So, one can take recourse to a Newton-Raphson and having an initial guess, and then once that will be the Newton-Raphson for a particular initial guess is converged, then one can put a outer loop where the initial guess will be given an increment plus 3, and the outer loop will be completed. So, if you calculate this 4 times, one will be automatically landing up with 4 roots of this governing equation. So, by taking recourse to a numerical method, one can really obtain the first 5 roots or first 10 roots of this particular transcendental equation. So, once we get that, then we will be formulating the time varying part. Tn is equal to C3 exponential minus lambda n square t, and u will be as a function of x and t will be nothing but n is equal to 1 to infinity Cn exponential minus lambda n square t cosine lambda n x. Okay. Now, the constant Cn has to be evaluated from the initial non-zero initial condition that at t is equal to 0, u was equal to u naught. So, let us go ahead with that. If we really do it, then we will be getting at t is equal to 0, u is equal to u naught, and therefore, u naught will be is equal to summation Cn cosine lambda n x, where n is equal to from 1 to infinity. So, we utilize the orthogonal property of the eigen functions. So, u 0 0 to 1 cosine lambda n x dx is equal to Cn cos square lambda n x dx. So, left hand side we will be getting u 0 sin lambda n divided by lambda n, and the right hand side we are having Cn by 2 0 to 1 2 cos square lambda n x dx. So, we can further simplify it sin lambda n by lambda n Cn by 2. This can be written as 0 to 1 1 plus cosine 2 lambda n x dx. If that is the case, then we can integrate it out on the right hand side, and what we will be getting is Cn by 2 is equal to 1 plus sin 2 lambda n x divided by 2 lambda n 0 to 1. So, you will be getting Cn by 2 1 plus sin 2 lambda n divided by 2 lambda n. Now, we can put sin 2 lambda n in terms of, we can express sin 2 lambda n in terms of tan lambda n, and we have the equation lambda n tan lambda n is equal to beta, and we can substitute that, and we will be getting a simplified version of the coefficient Cn. If you do that, you will be getting u 0 sin lambda n divided by lambda n is equal to Cn by 2 1 plus 1 over 2 lambda n is equal into 2 tan lambda n. We are substituting cos 2 lambda sin 2 lambda n by tan lambda. So, 1 plus tan square lambda n. So, this will be Cn by 2 1 plus this 2 will be cancelling out. So, it will be beta tan lambda n will be beta by lambda n, that is the transcendental equation the eigenvalues must satisfied. So, beta by lambda n divided by 1 plus beta square by lambda n square. So, this becomes Cn over 2 lambda n square plus beta square plus beta divided by lambda n square plus beta square, and we can get the expression of Cn as 2 u naught sin lambda n divided by lambda n multiplied by lambda n square plus beta square divided by lambda n square plus beta square. So, this is the constant, and the complete solution is u is equal to summation n is equal to 1 to infinity Cn exponential minus lambda n square t cosine lambda n x, where n runs from 1 to infinity. So, that solves this problem completely. Now let us look into the some more problems. So, this completely solves up this problem. It is a, we can call it a fourth kind of boundary condition, where the boundary at x is equal to 0 is Neumann, and boundary at x is equal to 1 is a Robin mixed. Next, I will be taking up one more example in order to demonstrate the various types of solution using the separation of variable. the problem that I will be talking about, it will be again a practical problem where we will be having a Robin mixed boundary condition. It's a one dimensional transient heat conduction problem. This will be alpha. So this will be another example. Example 3. Let us say alpha del square t del x square at t is equal to 0. We have t is equal to t naught. At x is equal to 0, we have t is equal to t1, and at x is equal to L, we have a Robin mixed boundary condition k del t del x is equal to h t minus t infinity. That means at this boundary it is open to atmosphere. Whatever the amount of heat that has been transported here by conduction, that will be taken away by convection, where h is the heat transfer coefficient and t infinity is the ambient temperature. Now we make this equation non-dimensional such that one of the non-homogeneity will go. So x star will be x by L, and theta, the non-dimensional temperature, will be defined T minus T infinity divided by T0 minus T infinity. So let us put it in the governing equation. So this becomes del theta del t is equal to alpha del square theta divided by L square delta x star square. So this will be nothing but del theta del tau is equal to delta square theta del x star square, where tau is equal to L square t over alpha. Alpha t over L square. So tau is equal to nothing but, so this will be L square will be on the other side. So it will be alpha t over L square is the non-dimensional time. Now let us put in the boundary condition at tau is equal to 0 means at t is equal to 0 means at tau is equal to 0, theta is equal to theta naught minus t naught minus t infinity divided by t naught minus t infinity, that will be equal to 1. At x star is equal to 0, theta is equal to t minus t is equal to t1. So t1 minus t infinity divided by t0 minus t infinity. So that will be, let us say, theta 1, and at x star is equal to 1, we have a mixed boundary condition. So I think we will discuss it in detail. So at x star is equal to 1, we have minus k by L, this will be del x star, and this will be del theta, and that will be multiplied by t naught minus t infinity. So this will be equal to h t minus t infinity. So this will be so what is the definition of theta? Theta is equal to t minus t infinity divided by t naught minus t infinity. So it will be t naught minus t infinity times theta. So this will be cancelling out. So what we will be getting is del theta del x star plus h L over k times theta, and what is h L by k? It is called the Biot number. It is a non-dimensional number. It is a Biot number. It is a ratio of heat transfer coefficient divided by thermal conductivity. It is ratio of the thermal resistance by diffusion divided by thermal resistance by convection. So we will be having del theta del x star plus bi theta is equal to 0 at x star is equal to 1. So in this particular problem, we have two sources of non-homogeneity. So the non-homogeneity, two sources of non-homogeneity. So let us look into what are the two sources. So one is at initial condition at tau is equal to 0, theta is equal to 1. Another is at the boundary condition at x is equal to 0, theta is equal to theta 1. So I divide this problem, we call this as theta 1 naught in order to make it consistent. So I divide this problem into two sub problem. One is theta 1, another is theta 2, considering one non-homogeneity at a time as we have done earlier. So therefore theta 1, the sub problem 1 will be basically del theta 1 del tau is equal to del square theta 1 del x star square. At tau is equal to 0, theta 1 is equal to we put the boundary we keep that non-homogeneity intact and force the others to vanish. At tau is equal to 1, theta 1 equal to 1, and at x is equal to x star is equal to 0, theta 1 is equal to theta 1 naught, and at x star is equal to 1, we have the mixed boundary condition del theta 1 del x star plus bi theta 1 is equal to 0. Now, this particular sub problem, this is a well posed problem, well posed parabolic partial differential equation, and we have already solved in great detail how to solve this sub problem earlier. Now, let us look into the other sub problem. The other sub problem is for theta 2. So, it will be del theta 2 del tau is equal to del square theta 2 del x star square, and at tau is equal to 0, we keep this initial condition to be homogeneous and substitute the other one, x star equal to 0, theta is equal to theta 1 naught, and x star is equal to 1. We have the Robin mixed boundary condition del theta 2 del x star plus bi theta 2 is equal to 0. Now, again, since we have a 0 initial condition, this problem has to be divided into two sub problems. One is the time dependent part, another is the time independent part. So, we can constitute the governing equation of theta 2 s, that is a time dependent independent part, d square theta 2 s dx star square will be equal to 0. At x star is equal to 0, we have theta 2 s is equal to theta 1 naught. We associate the non-homogeneous part with the steady state solution, and x star is equal to 1 d theta 2 s dx star plus bi theta 2 s is equal to 0. Similarly, we formulate the other part, the transient parts. It will be del theta 2 t del tau is equal to del square theta 2 t del x star square. At tau is equal to 0, theta 2 t will be nothing but minus theta 2 s x star. There is a steady state solution of the steady state part, and at x star is equal to 0. Since we have associated the non-homogeneous governed boundary condition with the steady state solution, so theta 2 t will become homogeneous, and at x star 1 equal to 1, this becomes del theta 2 t del x star plus bi theta 2 t will be equal to 0. Now, again, this is a well posed problem of third kind, where the eigenfunctions will be the sign functions and eigenvalue will be coming from the transcendental equation that we have already looked before, and this will be straightforward part. We will be getting the straightforward the solution of the steady state part, and solution of the steady state part will be substituted here, and again it is a well posed problem and we know the solution of this. So, the complete solution will be obtained as theta is equal to theta 1 plus theta 2 s, which will be a function of x star only, plus theta 2 t, which will be a solution of this part. So, we will be constituting in this. So, we will be will be able to construct the complete solution of this problem. So, I am also almost come to the end of my end of our course. So, in this course we have learned about the solution of partial differential equations for the engineering problems, and we have already looked into the in detail the how to form what are the classifications of the partial differential equations. They are how to identify and define various boundary conditions, various partial differential equations. What is the principle of linear superposition. We have developed various theorems related to the standard eigenvalue problem, adjoint operator, and the properties of the standard eigenvalue problem, which will be having a infinite number of eigenvalues, and the eigenfunctions are orthogonal to each other. Various properties we have looked into. Then we have looked into the solution of separation of using separation of variable method for the rectangular coordinate. We have defined different kinds of sub problems depending on the boundary conditions. For example, first kind, second kind, third kind, and how to divide the problems into sub problems in order to take care of non-homogeneities in the boundary conditions. Then we have looked into the three types general solutions of the three types of partial differential equations, that is parabolic, elliptical and hyperbolic. Then we have looked into the two-dimensional problem, three-dimensional problem as well as the four-dimensional problem, and then we covered the two-dimensional and three-dimensional problems in cylindrical polar coordinate system as well as the spherical polar coordinate systems, which the engineers will be coming across quite often. So this course gives a basic fundamental background of the engineers, how to tackle the partial differential equations. Those will be appearing for different engineering applications, and how to solve them using separation of variables if the operator is a linear operator. Now, in an actual case, the operator may not be linear, the problem may not be linear. So, one can take recourse to the numerical techniques, which will be the time consuming as well as the computationally intensive, but as a first case, one can go ahead with one can linearize the problem, assuming the constant thermophysical and the transport coefficients, and one can go ahead with the solution of the separation using separation of variables as a first hand information of the complicated system. So, I hope this course will be useful to you for all the engineering students, and particularly for chemical engineering, mechanical engineering, aerospace engineering students. Okay, thank you very much.